So step 4 is the derivation of the element stiffness matrix. I will leave this part up to you. In this case, we have used the principle of minimum potential energy to derive the element stiffness matrix for this element. Yeah, so I will just only explain the concept. So what we do is we try to write down the total potential energy of this element as a function of nodal displacements, and we try to minimize we try to find the conditions such that where the total potential energy is minimized by simply finding the minimum of this potential energy function. So simply explain, the total potential energy is nothing but a function which corresponds to the displacements of the I, j, and m nodes, and we try to come up with the total potential energy, or we express the total potential energy, which is a function which contains the strain energy, and of course the potential energy due to the body forces, potential energy due to the concentrated loads, potential energy due to the distributed loads, and you try to come up with this function. You try to minimize the total function, and by certain mathematical relationships, by applying mathematical relationship, you can basically go through these steps by considering the body forces, the concentrated loads if they are applied, and distributed loads if they are applied, these different contributions. You will have different expressions for obtaining these different contributions, and what you do is when you add up, you try to minimize this total potential energy, and by minimizing the total potential energy function, we will be able to obtain the stiffness matrix, an elegant, let's say, stiffness matrix for the concentrated triangular element. So all these steps I have skipped based on your interest, and based on you can when you have time after the lectures, this is quite a powerful method which we did not discuss because it's out of the scope for the moment, but this is another method which we can use to derive when the systems get more complex. We can use this minimum principle of potential energy to derive the, or to characterize a system, or to obtain the element stiffness matrices of a system. Yeah, so even for a spring element, truss element, and of course beam element, we can use the principle of minimum potential energy to derive the stiffness matrices, but we did not discuss this because we use the direct relationship using forces and applied to consider the force equilibrium and of course the boundary conditions to come up with the solution. But when the elements get more and more complex, solving these equations, linear set of equations, becomes cumbersome, and it's quite hard. You cannot do this. Then the most elegant way to tackle these problems is to use the minimum principle of minimum potential energy. So if you're interested, you can go back also to spring element, truss element, as well as beam elements, and try to look up the derivation for the corresponding stiffness matrices using the principle of minimum potential energy. So what you need to remember at this moment is that we have applied the principle of minimum potential energy, which is clearly explained in this lecture note. You can go through this leisurely, and what you need to remember is the stiffness matrix for a constant strain triangular element can be written using the thickness, using the area, and the B matrix and the D matrix, the constitutive matrix and the B matrix. Using this set of matrices and of course mathematical relationships, we can obtain the constant strain triangular stiffness matrix for the constant strain triangular element. So what are the assumptions? There are certain assumptions behind derivation of this constant strain triangular element matrix. Certain assumptions are the elements have a constant thickness, of course. That is why we consider T here. T is the thickness thickness of the element. So as the finite element decreases, this should be more. So when the element thickness decreases, this condition should be more and more applicable, because when then we come close to the planar conditions, because when the thickness is larger, we thought that the plane stress condition can be considered when the thickness of the element is quite small, because the normal forces and the shear forces acting in the perpendicular directions are zero or can be negligible. So when the plate or the element which we consider has a very thin element is a very thin element, then we get more and more close to the plane stress condition. So as I mentioned before, this is nothing new. T is a material, I mean, from the geometry, you can get the thickness of the element. A and B are defined in terms of nodal coordinates. If you know the nodal coordinates, you can calculate the area of the, we just saw, we can calculate by taking the determinant of the X variant, the X matrix, we can calculate the area of the corresponding triangle. And the B matrix is nothing but a set of, it contains a set of values based on the nodal coordinates of the ij and m nodes. And D matrix is the constitutive matrix or the stress strain matrix, nothing but a matrix which includes mechanical properties of the element that we consider. The modulus of elasticity and the Poisson's ratio is considered. So yes, so this total element stiffness matrix can now be defined since it has let's say 3 nodes. It will be a 3 by 3 matrix. Oh, the small K matrix, we can write the K matrix using I and J nodes. So the first column corresponds to the ith node, the second column the jth node, and third row corresponds to the mth node. So where each, let's say, matrix, which is a 2 by 2 matrix, can be obtained using this relationship, which we saw here, 5.2.2. By substituting this relationship for each node, you can obtain 2 by 2 matrices and come up with all these elements using B matrix, D matrix, the thickness and the area of the triangular constant strain, the triangular constant strain triangular element matrix. So this is, since this is a 2 by 2 matrix, since K values, these matrices are 2 by 2 matrices. So this, since, because all these matrices are 2 by 2 matrices, the total matrix, the total stiffness matrix would be a 6 by 6 matrix altogether. Yeah, so it will be quite a large matrix. So here I have mentioned some important points. When we are so when we ever have distributed loads, we can use the nodal distributed, I mean, we can segment, we can use the equivalent nodal forces at the nodes, so to define concentrated loads at the particular nodes. So in the previous cases, when we analyzing beams, we saw how we can separate a distributed load into certain nodal forces. A similar way, we can using a similar procedure, we can use in this case, whenever there's a distributed load over or distributed body force over a element, we can separate it and attribute it as nodal forces, concentrated nodal forces. Okay, so if we do that, we can now relate the total stiffness matrix now, which is 6 by 6 matrix, to the corresponding nodal forces. So we have 3 nodes, I, J, and M nodes. Yeah, and we have 2 forces acting in X and Y direction, and we can relate it to the corresponding nodal displacement functions. Yeah, so in the next step is nothing but when you have uh, element stiffness matrix for a particular element, the next step we have to do is, when we are considering an assembly, you use the direct stiffness method and to assemblage the total matrix and to come up with a total global stiffness matrix. And by applying the proper boundary conditions, we will be able to find the displacement at each node. Yeah. So here we can see that how these different forces have been defined. Of course, in this case, there has been also an additional rotation of the element. So I, J, and M, 3 nodes, and the corresponding forces acting according to the local coordinate system. And since this has been like rotated with respect to the global coordinate system, further the total global, okay, when we are constructing the total global structure stiffness matrix, we have to also consider this rotation into account. So additionally, just like we did in the case of trusses, we need to take into the account the rotation of the matrix. Yeah. So what is the rotation of the matrix? You can recollect. So each X and Y, or each uh, nodal rotation, can be described using this sine and cos terms. This we already learned. So we have to consider this total rotation matrix also when we are, if our global coordinate system differs from the local coordinate system. So since we have a rotation here, let's say if we have a rotation here, we have to further multiply our element stiffness matrices using a rotation matrix before we assemble or the total global structure stiffness matrix. So now you can see we have further complicated the problem, not only by dimensions, by considering an extra dimension, by considering also an rotation. So I think by now it is more and more clear why we require a computer package, let's say a numerical package, in order to solve these problems. It is becoming harder and harder in order to solve using hand calculation, isn't it? So this is the intention. This is why we exactly need the help of a computer to solve complex problems. Because when we go up in the dimensions and we consider, let's say, plane stress and plane strain conditions, we need the help of a computer to solve such problems. That is, all these concepts have been applied and adapted or implemented in softwares like ANSYS, and you will be using these concepts when you are analyzing problems, or when you are applying boundary conditions, when you are selecting a element size element, when you are using constraint triangle elements, and you are using the ANSYS application package. All these underlying theory that we have discussed will be applied. This is what I wanted to say. Okay, then the next step would be, once you have the already rotated element stiffness matrix, then one can construct the total global stiffness matrix and apply the nodal displacement as well as the boundary conditions to find the nodal displacements. And once you know the nodal displacements, you can substitute and analyze the stresses applied at each node. Okay, we can, or else you can solve element forces, of course, based on the nodal displacement, since you already find the nodal displacements by applying that by considering the total structure. So it is the same principle that we will be following. Okay, after let's say a long set of derivation, so to say, a lot of information, let's try to now put this into practice. How can we really evaluate a element stiffness matrix for a simple concentrate triangular element for a plane stress element? For you to break some ice, so this will be an icebreaker for you all. Take down this equation, take down this problem. Yeah, so a simple triangular element, and you can see the nodal I, J, and M, which has been defined in the anticlockwise direction, are now 1, 2, and 3, given in terms of not I, J, and M. They are given in terms of 1, 2, and 3, and the corresponding nodal locations are given for this. For this concentrate triangular element, you are supposed to find the element stiffness matrix, and also not only that, to find the element stresses acting for this each element. So just try to give it a shot, take 1 or 2 minutes and try to, let's say, revise what you did now and try to find the values here, or try to find the element stiffness matrix and also the element stresses acting on this of when you if you are considering this problem. And of course you need to make certain assumptions when doing so. Let's assume that this problem is a plane stress problem, a very small thickness, negligible thickness, somewhere around 1 inch. Material properties are given. Okay, the Poisson's ratio is 0.25 and the modulus of elasticity is the 30 times 10 to the power 6 psi, and the coordinates are also given in inches, so you can work out this problem in using the imperial units. You don't have to convert. Okay, and also one assumption that you have to do is assume that the nodal displacements have already been determined and given to you by this value. So the at node 1, node 2, and node 3, these are the nodal displacement that you would observe for this problem. Yeah, so for node 1, node 2, and node 3, you see it's given in terms of inches. Now the next step is to obtain the element stiffness matrix. Just take 1 or 2 minutes and try to write down the equation which you require for obtaining the element stiffness matrix for this particular element. Then we can construct the corresponding or supporting element matrices based on the information given in this example. So since the equations probably might be already hovering inside your mind, just quickly go through the lecture notes or the note which you probably already took and write down the element stiffness matrix for a element, the concentrate triangular element. Then we can work out the solution together. Okay. The first step is quite logical. We have to define the concentrate triangular, the stiffness matrix for the concentrate triangular element, which is nothing but which is expressed using the thickness, the area of the concentrate triangular element, the B matrix, which is nothing but a function, or which is a set of coefficients which you obtain using the nodal coordinates of the element, original element, or the original position. D relates to the material properties of the element. So now you have to simply substitute these values to obtain the element stiffness matrix. Yeah. So first we know that in order to calculate the B matrix, we require beta and gamma values of, let's say, I, J, and M by substituting the local coordinates of the nodes I and M, or 1 and 2. Of course, 1, 2, and 3, you would get the corresponding coefficients for beta and gamma nodal at the first, second, and third node. Then, based on these values, one can construct the B matrix, because you already know this is 2 times A here. You already know when you take the determinant of the element stiffness matrix, or the X matrix, which you can find. You can obtain the just give me a second. I need to okay. Sorry. So now, since you already know the area, of the element, and you know the nodal coordinates, you can find the B matrix. And for the plane stress conditions, we already know some form of D matrix with the help of the modulus of velocity and the Poisson's ratio. We can use the corresponding form of the D matrix to obtain the value for the D matrix. Okay, we know the thickness, we know the area now, based on by taking the determinant of the X matrix based on the nodal coordinates. We already know the B matrix, which is a constant, of course, and the D matrix, which includes the material properties. When you substitute all the values, and you can see this is what you would get for the B matrix, the D matrix, and as well as the inverse of, let's say, the transformed version of the B matrix, and as well as D matrix and B matrix. Yeah. So this has been transformed version of the B matrix. So by solving this matrix, this is nothing but matrix manipulation, matrix multiplication. You would get the total, the stiffness matrix for the corresponding element that you have considered. So you can see even the derivation, even though the derivation was quite lengthy, when you're using this what you have learned, or when you're using this, when you're solving problems, it's quite straightforward when you're especially writing down the element stiffness matrix. So in order to evaluate the stresses, now we have to analyze the stresses given for the nodal, along with the nodal displacements. Yeah. So we know there are 3 stress contributions in the X, Y, and Z directions, and which can be expressed via the D matrix, B matrix, and we already know the displacement matrix, mind you. This has been given to you when you're working on the problem. So this has been given to you, so you don't have to solve for the displacement. In normal cases, what you have to do is you have to, based on the boundary conditions, you have to work back the displacements by considering the total structure, by applying the proper boundary conditions. You have to find the displacements of each node. But in this case, you have been given displacement for each node, and you substitute them, and with the help of the D matrix and the B matrix, you can work out the corresponding stresses applying in X, Y, and Z direction, as well as the shear stresses by solving this matrix. It's nothing new. Okay. So if we are interested in calculating the principal stresses, since we already know the normal stresses as well as the shear stresses acting along the, let's say, x, y, and z direction, we can simply use the equations provided in shown previously. Of course, you can recollect from the strength of material causes, the minimum and the maximum principal stresses can be obtained using sigma x, sigma y, and tau xy values. Yeah. So, and you can calculate the principal and principal stresses, as well as you can calculate the principal angle corresponding to the principal stresses. So why do we need to calculate these principal stresses? In your lab classes, you will see that you would use a special, let's say, yielding criteria. It can be von Mises yield criteria, which is based on these principal stresses. And based on these values, you can predict, or you can come to a judgment, make a judgment whether this material will fail or not, whether the component you are analyzing will fail or not. If the one means, if it means in the equivalent one means stress exceeds the material yield value. If it is the case, or if you're analyzing these principal stresses, you can use a certain criteria and see whether the material fails, or whether the under certain boundary conditions or not. This is what you will be doing within the lab classes. Yeah. So what I want to try to motivate you is that whatever you do with the program is already implemented using these equations, and you have already worked out here numerically, and you have done hand calculations to calculate, let's say, the principal stresses, and based on this, the normal stresses as well as shear stresses acting on certain elements, and based on that you can calculate the principal stresses, and you can come to a certain judgment whether the materials will fail or not based on your calculations. So the same thing is what you will do within the lab classes. The only thing is you will not consider one element, but you will consider, let's say, thousands and thousands of elements to analyze more complex geometries. And based on these assumptions, or based on your construction, you will make judgment whether these materials will fail or not. If it is failing, what, at what location will it fail, and under what boundary conditions will it fail, and what is the allowable stresses and strains for a certain complex geometry. Yes. So because we covered a lot of a very lengthy part, I will not go into, let's say, uh, another section. Of course, in the next section we will also look about, we'll focus about how we can tackle body forces or surface forces. Whenever there are surface forces applied on concentric triangular elements, how we can tackle them. And at the same time, let's then also apply some body forces and do write a solution, or tackle the problem for a plane stress analysis case, yeah, in the next lesson, to get some more hang of it. So let's analyze a bar or a beam which is subjected to plane strain conditions, and how the body forces can be applied, and how it can be, how equivalent nodal forces can be applied to tackle a distributed load. We can separate the distributed loads into certain nodes and tackle uh, 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 a plane stress problem using constant plane triangular element stiffness, elements. Um, we will be focusing this in the next lesson.